Hello, and welcome back to Lecture 6, where we're going to do Trigonometric Substitution Part 2. So in the first part, we were dealing with integrals that involve square roots. And in these square roots were terms that were already the sum or difference of squares. So they were already set up very nice for us, and then we can make a trig substitution. It's not always going to be like that. However, there is something that you may recall all the way back from Algebra 2 in high school called completing the square. So if we're not given a situation where an integral is a nice sum or difference of squares under the radical, we can turn it into that using completing the square. So this first part of the video, I'm just going to get you familiar with how to complete the square again. It's like Algebra 2 review. So let's take a look at some examples, and then hopefully it should all come flooding back. So my first example is going to be x squared plus x plus 1. And I would like to turn this into two squares. I'd like to turn it into the form it was before, where we were doing a squared plus b squared x squared, for example, or a squared minus b squared x squared. So we're trying to make it look something like that instead of just three terms like this. OK, so first thing you do is you look at what constant is in front of x squared, and usually we call this a, not to be confused with this a, but in Algebra 2 you call the leading coefficient a, so not to be confused with that a. And if a is not equal to 1, we factor out a. We factor it out from just the first two terms here. However, because there's nothing here, because it's just 1, we skip the first step. So now we need to look at the b term. And we need to take half of b, and we need to square it. And we're going to introduce that into the expression. So you could think of this as like step 1, and this is step 2. So the b term that I'm talking about, and again, not to be confused with this b. This is very poor constant that I've chosen. But in Algebra 2, you usually say b is the term in front of here. We're going to take that number, cut it in half, and square it. So this time, b is equal to 1, and b over 2 squared would be 1/2 squared, which is a fourth. So we take this and we introduce this into the equation, and you're always going to add this part. So this is equal to x squared plus x plus a fourth. Now I need this to equal the original expression, right? They're not equal right now. What would I have to add or subtract to get to 1 again? Well, it would be 3/4, right? And then I have the thing I started with. So make sure you have the thing you started with. And now, once you've added on this special term, you can go ahead and you can complete the square. So the b over 2 squared, once we've chosen that and added this here, you've made a situation where you can complete the square. So this right here is x plus a half squared. If you don't believe me, FOIL it. And then I have this plus 3/4. So usually you're done here. We've basically completed the square. As an optional bonus, what you could do is you could say this is something squared. And then what is this technically? What would you have to square to get this? It would be the square root of 3/2, right? So you could write it like that just so you could really be prepared for the situations we're going to be involved in. But either one of these is fine. So now I've turned something that was 3 terms into something squared plus something squared. And that's called completing the square. That's all it is. So we're just going to turn it into a form we can use later. Let's look at another example. So my next example is going to be 2x squared plus 8x. Let's go through the steps again. This time, a is 2. So I actually will do my first step that I didn't get to do over here. You factor that out of just the term with x squared and x. So if you factor it out, you get 2x squared plus 4. And when you factor something out, I like to leave myself a space, because I'm about to introduce something else in here. So they're equal. So now what I need to do is I need to figure out, OK, well, what is half of b? So we need that, and we need to square it. So b this time, the number in front of x, after I factored that 2 out, is 4. half of 4 squared is 4. So that's what I need to introduce right here. However, you can't just add 4 here and still have the same thing. So now, if you distribute, you would get 8. I overcounted this by 8. I've introduced an 8. So you need to subtract off 8. And now it's equal to the thing above. So let me move this over. This is b squared, or b over 2 squared is 4, right? That's just like a separate thing. I added 8, so we need to subtract 8 to keep it just like it was before, right? So just make sure you introduce the number that keeps it balanced. Now here I have 2. The thing I created is the perfect square. So this is the step where you complete the square. So the only difference with this case and the other one, you've got to be careful with these parentheses. And you just make sure you double check your work as you're going. This is x plus 2 squared. If you don't believe me, FOIL it. And this is minus 8. So in algebra 2, you'd kind of be done here. But you can rewrite this to really show that it's something squared times something squared. So what I would do for this one is I would say that the first thing is this squared. If you take the square root of 2 and square it, you get 2. And this one already was squared. And now this thing, just like before, 8 doesn't really have a rational square root. So like what you do is you just do the square root of 8 squared. And again, both of them are pretty acceptable. You should be able to see what to do in either case. But now I've taken this thing that wasn't 2 things squared, and I've turned it into something squared minus something squared. And notice because this one was a minus, it would fall into this case. And you should recall that this was our case for sine, right? And this one is something plus something squared. So when we do our substitution with that, it's going to be a tangent. So hopefully you've got the 3 cases memorized at this point. I'm going to do one more because it's so important to be able to do this. This is how you start the more difficult problems. If you can't start it, then you won't be able to get the right answer. I really do encourage you to stop the video at this point and try this one. This is the last one I have for you. So you should try it and then come back to the video and see if you can, if you match what I get. But I'm going to go ahead and do it. What I like to do is I like to rearrange this. I probably should have told you guys that before I went and had you guys go do it, but you don't have to. But as a personal preference, I like to rearrange it from descending. So it's like x squared x3. This time a is negative 4. So factored out of the first 2. You get negative 4 on the outside. We get x squared minus x plus something. We also get this plus 3 now. That's just like coming along for the ride, basically. And now I need to take half of b and square it. b is that number in front of x here. It's negative 1. So if I take negative 1 over 2 and square it, I get a fourth, just like I did before. You're always going to add this quantity, though. It doesn't matter if it was negative. The squaring makes it positive. But now, what did I do? From here to here, I introduced negative 4 times 1/4 is a negative 1. I decreased this by 1. So to offset that, I need to add 1. So the negative 1 plus the 1, they cancel, and you go back to where you started again. So I didn't change anything. So remember, you have to kind of offset what you did. I'm going to rearrange this. This is 4 right here, the constant. It's 4. That's one term. And then minus this 4. And I'm going to complete the square. So this should be something squared if I've done this right. It's x minus 1/2 squared. And then again, this is a perfectly acceptable answer. You could go even one step further and say this is 2 squared. That's like the a here, minus 2x minus 1/2 all squared. So now I really do have this thing squared plus or minus this thing squared. Again, I like either one of them. It's fine. But this, the last one I'm writing in each line, even though it looks weird, that really lets you explicitly see which one's A and which one's going to be B when we do our substitutions in just a second. So I hope that helped with completing the square. If you're still struggling, I'd go look up just some Algebra 2 textbook or something like that, or a YouTube video. Get really comfortable completing the square, because the difficult problems are going to call for it. OK, I'll see you in just a moment. We're going to do 2 harder trig sub problems now that you have this down. So I'll see you in just a second. All right, everybody, welcome back. So in this part of the video, we're now going to be using our technique of completing the square that we just reviewed to evaluate these two tougher trigonometric substitution problems. And over here, I've given us a reminder of what the substitutions are. Nothing's changed except for I changed all the x variables to y's, but it doesn't make any difference. You'll see in a second why I needed to do that. But they're the same three that you memorized from the last video. All right, so we're going to start with this problem. You see there's a radical involved here, so it could be trig substitution. However, right now it's not something squared plus something squared. There's three terms. So we did the work just a few seconds ago in the other part of the video. We completed the square for this, and we said, if I look at my notes here, we said it was x plus 1/2 squared plus root 3 over 2 squared. That's what we said that that was. So now, if you compare this to the stuff I've got going on over here, notice I couldn't use the same variable because I'm looking for something squared times a b squared, and I called it y. So this right here is my y squared. It's the thing that's getting squared. It's the variable part. So I'm going to be using the tangent substitution for this because there's a plus symbol here and there's a plus symbol here. So b this time is 1 right there. And then a, the constant that's getting squared, is root 3 over 2. I've got it in parentheses right there. So now let's make the same trig substitution we were using in the other video. So I'm going to say x plus 1/2, this thing getting squared, is equal to a over b minus, b is 1. And then we're going to use the tangent substitution because this falls under the third case over there. Now, in this case, I'm going to go ahead and solve for x. So that involves subtracting the 1/2 to the other side. I see in the original problem I'm going to have to substitute in what x is, so I'm going to do that. I'm also going to need dx because that's here as well. So the derivative of this is going to be root 3 over 2 secant squared is the derivative of tangent, and then this will just be 0, d theta. And then one other thing I'm going to do is I'm also going to solve for tangent. I'm going to need it later. So let me solve this for tangent. Let me start from the beginning here. I'm going to solve this equation for tangent so that I'm going to multiply both sides by 2. I'll get 2x plus 1 equals root 3 tangent. And then divide both sides by root 3, and I get 2x plus 1 over root 3 is tangent. And just remember, tangent is opposite over adjacent. So I'm just going to need that later, which is why I've got my list of information right here. You know what? I'm going to draw the triangle right now. Let's just get it all knocked out at once. I know this is a little out of order, but you guys are used to these problems by now. If this is my angle here, tangent is opposite over adjacent. So opposite is going to be 2x plus 1. That's what this side's going to be. Adjacent is going to be root 3. And then here I get the square root of, and then it would be 2x plus 1 squared plus radical 3 squared using the Pythagorean theorem. And if you want to simplify this, this is 4x squared plus 4x plus 4. If you simplify that, and you could even further simplify that and just say that this is, if you factor out the root 4, it's 2x squared plus x plus 1. So really, this is the hypotenuse over here. OK, so that's me taking care of all my bookkeeping. Let's go ahead and continue with this. So let's make the substitution. X right here, I have it in this second equation. X is going to be radical 3 over 2 tangent theta minus 1/2. Dx right here is the third line. This is going to be radical 3 over 2 secant squared theta minus, oh, sorry, that's d theta. I'm just going from this equation right here. And now, in the denominator, I have x plus 1/2. I've said that this is root 3 over 2 tangent, and I'm going to square it. So if you square that, you get 3 over 4 tangent squared theta plus, and then this squared is 3 over 4. OK, we need to keep going with this until we get an answer. So I see that this simplifies. What I'm going to do first is I'm going to just try to simplify what's in here. So I get the integral of radical 3 over 2 tangent theta minus 1/2. This is a radical 3 over 2 is a constant, so I'm going to bring that out front, just like that. And then I have secant squared theta d theta. And then here, if you factor the radical 3 over 4 outside, you have in the denominator radical 3 over 2. So that comes from factoring it out of the radical here. And then if you do that, what's left in here is tangent squared plus 1. So what I've done here, I'll write it right here, is I've factored this as radical 3 over 4 tangent squared plus 1. That's what I did, is I brought the 3 fourths out. And then this right here, what's that equal to? That's secant squared. OK. So these two cancel out. And I have the integral of radical 3 over 2 tangent theta minus 1/2. Radical secant squared is going to be secant. So I have a secant here, but I still have a secant in the numerator. And now I'm going to take that and distribute it to each of these. So I get radical, this is 3 over 2 tangent theta secant theta minus 1/2. So I'm splitting this into two integrals, and I'm distributing this secant. This is minus 1/2 secant theta d theta. Each of these are within our rules, so we are able to do this one now. So the integral of secant tangent is secant. That's the antiderivative. So you get root 3 over 2 secant minus 1/2. And if you have your note cards and you've memorized the rule for secant, we did this. The integral of this is the natural log of secant theta plus tangent theta. And then this would be plus c. So each one of these is an integration rule, thank goodness. And then the very last step, as with all of our other problems, is you go back and you substitute into where you have to substitute. So secant right here. Secant is 1 over cosine. And cosine is adjacent over hypotenuse. So this one is this one is hypotenuse over adjacent. So my hypotenuse is this. It's the 2 radical x squared plus x plus 1. Adjacent is going to be root 3 minus 1/2. This is ln of, I just said what secant was. It's this. It's 2 radical x squared plus x plus 1 over root 3. And then tangent, we had that, didn't we? It's over here. Tangent's this. I mean, you could go to the triangle, but we already know what tangent is. That's the 2x plus 1 over root 3. And this is plus c. So this is our final answer. So you can see it's a little tougher because the substitutions can be a little tougher, but the overall process is the exact same. So I see just a few things you could do with this maybe to make it look nicer. See how these 2's could cancel, and also the radical 3's, they could cancel. And then this is a common denominator, right? So you could like kind of add these and combine them into like one fraction. And a 1/2 power comes up, so that could be like a radical as well. So there's some ways to rewrite this and make it look better. I will leave it like that though. OK, I'm going to start this next problem in just a moment, but you might want to try it first. All right, welcome back. Did you give this one a try? I'm going to use all of my board space here to probably finish this one. I'm so worried I'm going to run out of room. But let me start this one. I'm going to start off the same way as the other one. So this is x squared dx. And then I need to take this thing that's a trinomial and turn it into a perfect, like a sum of squares or difference of squares. So if you just go back to our completing the square example, we did this one as the last one. So this one was equal to, if I go back and look at what we did, we ended up getting 4 minus 4 parenthesis x minus 1/2 squared. So So that's how we completed the square for that one. Okay, so we need to make choices. I'm going to do some of that up here, I think. I'm going to try to conserve space. So here I have a constant minus a variable part. Which one of these three cases is that? It's the first one. This is a constant minus a variable part squared. So this time the number getting squared is 2. So I'm going to say a is 2. B is also 2, because that's in front of the variable part. So B is also 2. So we're going to have these. And then if we use this substitution, that tells us that this y right here, the x minus 2, sorry, x minus 1/2, this is equal to a over b, which is 1, sine theta. And I'm going to do all the kind of similar busy work over here just to have the stuff ready to go, if you know what I mean. So first thing I'm going to do is I'm going to say, well, x is equal to sine theta minus, or plus 1/2, right? If I solve that for x. And that also means that dx is just equal to cosine theta d theta. And also, if I just want to rewrite this in a nicer form, so let's just continue this equation. The common denominator would be 2. So 2x minus 1 over 2 is actually equivalent to that as well. And that just lets me see that sine is opposite over hypotenuse, right? I just kind of want to see that when I draw my triangle. Let's use this space here, this real estate, to knock that out. So sine is opposite 2x minus 1 over hypotenuse, which is 2. And then this, if you did Pythagorean theorem and you worked it out, it turns out this is 4 minus. And then this is 2x minus 1 squared. OK, so then from here what I'm going to do is I'm going to start substituting now. I basically did all my busy work. Now I can plug everything in and just go for it. So x squared. Here's x. So I'm going to square that. It's the second equation here. So I get sine theta plus 1/2. This is all squared. What is dx equal to? It's just cosine theta d theta. So that part's not so bad. This is where I'm going to use my substitution. So I get 4 minus 4. And then x minus 1/2, I said that's sine. So if I square that, I get sine squared. And this is to the 3/2. So then this is sine theta plus 1/2 squared cosine theta d theta. I don't want that to interfere with my picture. This, go back to other parts of the video. You should have your Pythagorean identities down by now. A constant minus sine squared, this is going to be cosine squared. And how many of them is it? It's 4, because they all have a 4 coefficient. So this is the same thing right in here as 4 cosine squared theta. Remember, it's to the 3/2 power. So it's some kind of root, but it's not the standard square root. It's a 3/2 here. Well, let's continue. So here I'm just going to do sine theta plus 1/2 squared cosine theta d theta. I'm going to take 4 to the 3/2 power. And the way I do it is I take the number on the bottom first. Square root of 4 is 2. And then 2 cubed, that 3 is 8. So I get an 8 in the denominator. I'm going to instantly throw that out of the integral. I don't want that there. And then 2 to the 3/2 power, a power to a power, that's 3. So cosine would be cubed, but I have a cosine on top already. So cosine divided by cosine cubed, what that actually allows me to do is just delete one of them. And now I just have cosine squared in the denominator. OK, now from here what I'm going to do is I don't see anything left like that I can cancel. So now I'm going to have to FOIL this. So if you FOIL the top, it's sine squared plus half sine plus half sine is sine theta plus 1/4 would be the last term there over cosine squared theta. The good news is everything is over one term. So what I'm going to do to make the work easier for me is I'm going to split it up. I'm going to make this into 3 easier problems for myself. So 1/8 in front of the entire thing. The first integral is sine over cosine, which is tangent squared theta, plus, here I have sine over cosine squared here. So sine over cosine is tangent, but I have a remaining cosine in the denominator here, so 1 over cosine is actually secant. And you can see what I'm about to do with that, right? Like, that's why I did that right there. This is going to be 1/4. My last integral is 1/4. 1, there's nothing here, right, up here, so 1 over cosine, that's secant, but I have 2 of them. 1 over cosine is secant, so I have secant squared here. These all have d theta, d theta, d theta, or d theta. 1/8 is in front of every single one of those, and that's what happens when I split them up. Some of these are easier than other ones. I think we actually already did this one. So remember that tangent is just secant squared minus 1. So that's a good strategy for the first integral. The second integral, integral of secant tangent is secant, because that's its derivative. So that's secant. 1/4, and then what function has secant squared as its derivative? Well, this one's just tangent theta. And then finally, since I'm at the end of the line, I'm going to put a plus c, but I still got to take care of this one. So I get 1/8. Integral of secant squared, again, is going to be tangent theta, minus integral of 1 is theta. And the way I did this, I already took care of the easier ones. So this one was just secant theta plus 1/4 tangent theta. And then this plus c is just some constant. It's just going to move outside of all of that. The very last step is I need to go ahead and plug all these back in. So notice these two go together. So I actually have 5/4 tangents. So I have 5/4, and I need to plug in what tangent is. So tangent is 2x minus 1 over this radical right here, radical 4 minus 2x minus 1 squared. So that takes care of the tangents here. What is secant equal to? Well, secant is ha, right? Because cosine is adjacent over hypotenuse. So secant is ha. So this is 2 over this, the radical 4 minus 2x minus 1 squared. And then the very last thing it looks like I need is theta. And I might need a little more room than that. I was being kind of optimistic there. So I need to know what theta is. To get that, we need to go back to the original equation. So look up here. Look at that equation. Sine of theta is this. So to solve for theta, you take sine inverse of both sides. So this would be sine inverse of 2x minus 1 over 2. And then that is the complete answer. That's everything. So you could do similar things like I did with the other one to simplify. You could finally take that 1/8 and distribute it to everything. You could get a common denominator, I guess, by multiplying by the 4 and then this radical to all of the terms. I'm not going to do that because, as you can see, I am very limited in space here. But this is, for all intents and purposes, this is correct. You can play around with it as you want, but that's the end of the problem, thank goodness. OK. So as you can see, these things can get very, very tricky, and there's lots of stuff going on. I can't even see you over all the stuff. But I hope this helped you. Please email me if you have any questions, and I will see you later. Thanks for watching.